Imagine waking up. You look out the window. The sky is a pale, dusty pink. The ground stretches out in every direction, rust red, rocky, and completely still. There is no wind you can hear, no birds, no ocean, nothing alive. You are 140 million miles from Earth. The question is not just whether we could get there. The question is whether a human being could actually survive, long-term, on a world that seems designed to kill us. And the answer is far more complicated than the headlines suggest. Of all the places in our solar system, Mars is the one that keeps coming up. And that is not an accident. Mars has days that are almost exactly as long as ours, 24 hours and 37 minutes. It has seasons. It has polar ice caps. It has a surface you could theoretically walk on. Compared to Venus, which has acid clouds and temperatures hot enough to melt lead, or the Moon, which has no atmosphere at all, Mars looks almost reasonable. Almost. The average temperature on Mars is around -60 degrees Celsius. The atmosphere is about 1% as thick as Earth's, mostly carbon dioxide, with almost no oxygen. The air pressure is so low that if you stepped outside without a suit, your blood would begin to boil within seconds. Not from heat, from the drop in pressure. And yet people are seriously planning to go there, not in some distant science fiction future. Now, within decades, maybe sooner. So what would it actually take? The first problem is just reaching the place. A trip to Mars, with current technology, takes somewhere between 6 and 9 months, depending on where the two planets are in their orbits. You cannot just leave whenever you want. The launch windows only open every 26 months, when Earth and Mars align in a way that makes the journey remotely fuel efficient. That means if something goes wrong after you leave, you cannot turn around. There is no rescue mission coming. You are committed. 6 to 9 months in a tin can. Weightlessness the entire way. That does something to the human body. Muscles waste, bones lose density. Vision can be affected. There is evidence that the fluid pressure inside the skull shifts in microgravity in ways we do not fully understand yet. And then there is radiation. Earth's magnetic field protects us from the worst of what the sun throws at us. In deep space, that protection is gone. On a round trip to Mars, a crew would absorb a significant radiation dose. Estimates suggest it could be equivalent to several years' worth of the safe annual limit for radiation workers on Earth. You arrive on Mars already weakened, already irradiated, already months away from help. That is just the journey. Now you are there. You step out, in a suit, obviously, onto a world that has not seen liquid water on its surface for billions of years. The suit itself is a critical problem that often gets glossed over. Spacesuits today are bulky, rigid, and exhausting to move in. Imagine doing construction work, which is what building a Mars base requires, in a suit like that every single day, in a low-gravity environment where you still have to be careful not to rip or puncture the one thing keeping you alive. The habitat has to be pressurized, it has to be heated constantly, and it has to be shielded from radiation because Mars has no global magnetic field and its thin atmosphere stops almost nothing. One solution researchers have explored is building habitats underground, or covering them with thick layers of Martian soil called regolith to act as shielding. Then there is dust. Mars has global dust storms that can last for months and block out the sun. If you are relying on solar power, which is one of the main proposals, a long dust storm could be catastrophic. The Mars rovers have dealt with this. A human crew would face it on a completely different scale. Here is where it gets interesting. Mars has water, not lakes or rivers, but water ice, locked in the polar caps and buried in the soil in certain regions. Getting to it, purifying it, and using it is a massive engineering challenge. But the water is there. There is also a concept called in situ resource utilization, a phrase scientists use to mean using what is already on Mars rather than shipping everything from Earth. The Martian atmosphere, thin as it is mostly carbon dioxide. With the right equipment, you can split that CO2 and combine it with hydrogen to produce methane, which can be used as rocket fuel. NASA's Perseverance rover actually tested a small version of this process called MOXIE, which produced oxygen directly from the Martian atmosphere. In theory, A Mars colony could eventually produce its own fuel, its own oxygen, and grow at least some of its own food, in sealed, pressurized greenhouses under artificial lighting. In theory, the gap between a successful lab experiment and keeping 50 humans alive on another planet is vast. Every single system has to work. All of them, all the time. There is no hardware store on Mars. But here is the thing that technical people sometimes skip over. Humans are not just bodies that need oxygen and food. We are social. We are psychological. We evolved over millions of years in a world with seasons and sunlight and open spaces and other people. What happens to a crew of 6 or 8 people, locked in a habitat the size of a large apartment, for years, on a planet where going outside requires a full spacesuit drill with a 40-minute communication delay to Earth? Analog studies, where researchers live in isolated Mars-like conditions on Earth, have shown real psychological strain, tension, conflict, depression, motivation, collapse. And those people could leave. A real Mars crew could not. This is not a small footnote. This might be one of the hardest parts of the whole problem. Selecting the right people, designing the right habitat, building the right social structure, these are not engineering problems. And we do not have clean answers yet. SpaceX has said publicly that they want to land humans on Mars within this decade. NASA's own roadmap has been more cautious, talking about the 2030s and 2040s as realistic windows for crewed missions. Both of those timelines assume an enormous amount of things going right. Starship completing development, life support systems being proven, radiation solutions being figured out, political will and funding remaining consistent over decades. None of that is guaranteed. But here is what is also true. The pace of progress over the last 10 years has been genuinely startling. Reusable rockets were considered nearly impossible not long ago. We now land them routinely. The MOXIE oxygen experiment worked on another planet. Mars orbiters and rovers have mapped the surface in extraordinary detail. The pieces are coming together. Slowly. But they are coming together, so could humans ever live on Mars? Yes, almost certainly, eventually. But not easily, not soon, and not without solving problems that we have not fully solved yet. Problems of radiation, of psychology, of long-term life support, of what happens to a human body after years in low gravity. The honest answer is that we are closer than we have ever been, and further than the headlines sometimes imply. Mars is not a backup Earth. It is not a plan B waiting to be moved into. It is one of the most hostile environments in the solar system, and making it home would be one of the greatest achievements in the history of our species. But that is also exactly why people keep working on it. Because some problems are worth solving, not despite how hard they are, but because of it. If you want to keep exploring questions like this one, subscribe. There is a lot more universe to get through. Next time, what would actually happen to your body if you got too close to a black hole? The answer involves something called spaghettification, and it is exactly as strange as it sounds.